Welcome to the AI Show. I'm Scott Stephenson, co-founder of Deepgram. With me is Jeff Ward, a.k.a. Susan.
Hi, all.
He's a Navy pilot, acclaimed dad joke writer, and AI scientist at Deepgram. On the AI Show, we talk about all things AI. What is it? What can you do with it? How does it affect you? Where is it going? We are live and ready to answer your questions. Comment on YouTube and Twitch or tweet at Deepgram AI to join in. Today we're asking the question, the very big question.
Big question.
How do you use a neural network in your business?
Oh.
So for like realsies, how do you use it?
Yeah,
right?
let's just talk about what people think of as neural networks and simple ones. There's sort of the classic one. The very first thing you ever build when you're learning how to deal with this stuff is like the MNIST digit predictor. Are you familiar with this?
Yep.
Scott?
MNIST.
It's like Modified National Institute of Science and Technology.
Something like that. Handwritten digits.
Yeah. Handwritten
28
digits.
by 28 pixels.
Exactly.
Grayscale.
Grayscale. Basically, they're handed to you on a silver platter.
Yeah.
And
centered.
Absolutely useless without a massive ecosystem around it to feed those digits into you in the perfect way.
What do you mean?
Well, I mean, you don't just take a picture of a letter and suddenly,
everything works?
Everything works?
Yeah.
Yeah.
Not that simple, right?
It's definitely not that simple. I mean, how do you take something like, a task of digit recognition? How do you break it down? How can you use deep learning to actually make an effective, useful model and create a tool that you can use in some meaningful way?
So like in the real world,
Yeah.
you have a task and you want to do something with a neural network. In this case, it's like I have a camera and I want to take a picture of something, essentially, or maybe a video camera, and I want it to figure out what is written on some letter or something like that. And you have handwritten digits, just the digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And tell me what the digits are. Simple task, right? A human can tell you right off the bat. They can just read them right off.
Exactly. And so this is sort of the difference between accuracy in the machine learning world and utility. You could have the most accurate classifier in the world.
Yeah, for a specific data set on a specific task.
But it's completely useless because you can't feed it that data in the real world.
Yeah.
Right?
So like if you want to send letters to the right place at the post office or something, and you want it to be mechanized, but people have handwritten everything. And so, hey, hard problem. You used to do it with humans. Now you want to do it with a machine.
Yeah. So that's the core idea for today is how do we actually create a machine learning model or use neural networks in a real world situation there. So we've got a great example there, the digit recognition on a letter or something like that. But what about also, I guess in the news there's talking about license plate scanners and stuff like that. What would it take to actually build something like that? How do you actually turn an idea, hey, I need this, and use deep learning in there? What are kind of your big idea of what you should be thinking about?
Yeah, you have to think about what's my data set, right? And that data set has to be at least kind of close to the task that you're trying to accomplish. Is it pictures of handwritten digits that are centered and perfect? Or is it pictures of license plates on cars that are driving down roads at like oblique angles with lots of light on them or smoke or something like that in the way, right? And okay, if you have those pictures, fine, but do you have them labeled by a human, and are they properly labeled? And are they centered or not? Are they all blown out and all white? Are they too dark? Do they have a big glare in them, et cetera, right?
Yeah, I mean, just that first step, we've talked about data so many times. Getting
very important,
very incredibly important. But it's important not only just to have data, but data that represents the production environment that you're going to be in. It's all well and good to have, say, for instance, license plate data, but if it's not taken in a meaningful way, i.e. it's staged with professional cameras and all these different, is that going to be as good of a data set as, no kidding, I'm actually taking footage from the real world and from the equipment that I expect to use. And, dealing with it that way. You know, not the version that is pristine, but the version that's already gone through all the whatever codecs have had their hands on it.
It's been compressed.
It's been compressed. It's been mangled.
Yep.
You know, why is it? By the way, why is it that whenever you see video like that, it's just
It's always crappy.
Absolutely the worst. It's
Shot by a potato.
Yeah. I mean, it's like Bigfoot. Magically, whenever Bigfoot shows up, it's on the worst video equipment ever.
Yeah.
But you got to think you're about to take pictures of Bigfoot.
Yeah.
And you need to recognize it, and you're going to have that quality. You know?
Yeah.
So it's.
Yeah, but you also have to be careful. Like, don't try to boil the ocean. You don't have to get every single angle and every. Hey, is it snowing? Is it raining? Is it whatever? Okay, you know what? Get verticalized. Get one thing working pretty well first, and then you'll start to see the problems crop up. But maybe 80% and 90% of your solution is already there, and then you tackle those problems later. You don't have to do everything all at once.
Yeah, and that's also another key thing here is be prepared for iterations on everything.
Iterate.
You know, get your first hour of data just so you understand kind of formats and how you might be processing and dealing with it before you spend tens of thousands of hours and umpteen $1 million collecting data that you then find out is not quite right. That's really heartbreaking.
Yeah, you can't just guess the answer from the outset. It's too hard.
It's gradient descent.
Yeah,
right? You
gradient
assess,
descent.
take a step, assess, take a step, assess, take a step.
Yep,
it's pretty classic.
Yep.
But so
what do you mean by gradient descent?
I've heard of this thing.
Yeah,
gradient descent. The basic algorithm that the huge chunk of machine learning uses to train neural networks. Like I said, I was giving the example there of assessing, taking a step, assessing, taking a step. The assessment stage is using what's called the gradient, and that points in a direction that might be a good way to go for your weights.
So like as an example, if you're walking around in a hilly terrain and it's your job to find water, you might want to start walking downhill.
Yes.
And so what do? You look around at your feet and you think like, oh, well, the hill is sloping that way. I should go that way. But does that necessarily mean that water is going to be that way? Not necessarily. But if you keep going downhill, if there's water around, it's going to be around there. Yeah. That gets into the discussion of maybe you're in a local optimum, meaning a local minimum in this case, right? And you might need to go over the next ridge and then find an even lower hole somewhere. But still, this is gradient descent. You're looking at the slope and you're moving along that path.
Yes. So gradient descent applies to machine learning, but it also applies to life. And it's a great process technique that, really works well. But so we were talking about data there and gathering data and the ideas behind, don't jump whole hog right away. You've got to make sure all that. But the next kind of step, another kind of thing to think about is along the lines of data is your inputs and outputs, right? When you're designing a system that's going to be useful, you're really actually thinking, how am I going to use this thing? You've got to think the data you're going to feed it, and the data it needs to be fed in order to predict some answer that you can then use to do something with. So we'll just very briefly think about the MNIST style digit classifier there. Its data inputs are a 28 by 28, grayscale centered
pixels,
digit,
white and black and gray.
How do you build that? You've got a whole ecosystem surrounding that, which it's got to find where the digits are at. It's got to parse them out and do all those different things. That's probably a harder task.
You're talking from like wild data.
Yeah,
like, hey, I've got a whole bunch of pictures. I'm starting out with 10 million pictures, but I'm going to whittle it down to the 60,000 that are actually my data set that I'm going to use to train.
Well, yeah, I'm just saying that when you're thinking about a production environment, I've got these cameras. How am I going to get to the classifier itself or to the network itself, the data into the shape and form that it was trained on, in order to make the prediction that I'm going to then use back out there. And if you find that the task of doing that is a lot harder than the model itself, you're probably right. The real world is not well normalized.
Yeah. If you get your data set right, you get your tools right, you pick your model architecture correct, you get your input and output set correctly, the training's actually pretty easy. You just say, like, go.
Yeah, well, I mean,
for the most part.
you
Compared to gathering all the data and all the like the little fidgety things you have to figure out.
yeah,
You know,
once you can kind of encapsulate the problem, that's really what we're talking about here.
Define the
Encapsulating
problem well.
Yeah, you need to define that problem, and again, going back to the iterative idea here, you'll find that you started collecting some data, and then you started designing inputs and outputs and a model behind it, and you realize, hey, maybe those inputs and outputs in that model can't work with that data, so you need to adjust, and you go through this iterative system, but you always have to have an eye with, I can't do anything that the real world doesn't support. And that's what a lot of people lose sight of when they're learning how to do these tools the first time.
it has to work for real in a real setting.
Yeah, I mean they're given these pristine data sets that have well encapsulated, some simple problem or even a complex problem. But I've personally spent 2 weeks working on one data set just to whip it into shape to be usable. And it's a really hard task to get the real world to be bent and shaped into something that's usable by your particular model. So keep that in mind when you're thinking about a usable model.
So like let's go from beginning to end for like a simple system. Say you have a dash cam in your car and you want it to detect license plate numbers and like display them on a display in your car. So you're like a police officer or something, right?
Yeah.
And
Officer Susan,
reporting for duty, and you're driving around in your car. You have a dash cam, and you want to like get a text, or you want to display on your screen or something like that of all the license plate numbers around you. Like, how do you build that system? Okay, you have the camera. Then what? Yeah, well, not even then what. The camera is, what is it doing? It's looking at an optical signal in the world. It has a lens. It's taking in light, and it's digitizing it. So that's really important. You have to be able to digitize the thing that you're actually trying to measure. It's pretty hard to measure people's thoughts, right? Other things that you could think about, very hard to digitize. But taking a picture, we've got that one. Use a camera.
Yeah, use a camera. So, like you said, you've got to digitize that. You got to be able to put it into some sort of portable processing system if you're doing this real time.
Yeah. So maybe it's hooked up to a USB. That dash cam is hooked up to a USB cable that goes to a computer.
Yeah.
And that computer is just like saving an image, 30 of them every second, just saving all of them and just building up tons of data.
Which again, going down to the question about inputs and outputs, we'll just take a base one here. Are you going to try to figure out something over time, or you treat each image individually? These are basic, simple.
You have 100 pictures of the same license plate. Do you want 100 notifications of that license plate, or just one?
So the image classification world has gone light years, just massive leaps forward since the original work on MNIST and what everybody's familiar with, making a simple multi-layer network to recognize digits, but in general you're going to have to find some way of taking that image that you've digitized.
It's a big image,
you've been able to feed into some engineering solution that takes on either takes a picture every n seconds or as fast as it can be processed, and then looks for the next one. Takes all that, feeds it in to something that's going to probably normalize the image for light, and do some techniques for basic image processing to take care of a whole lot of
try to
stuff.
make it not too dark, not too light.
Just the more you can normalize your data, the less your neural network is going to have to work, which is a great thing because it's going to get accuracy is going to go up there.
Sure, but you have a camera and it's got a pretty big view, and a license plate could be anywhere inside.
Exactly. So you're probably going to have to, again, go into something that's going to detect where license plates are at.
So you probably have two systems.
Yeah, at least.
One that's a license plate detector.
Yeah.
It just says, I think a license plate is here. But that's looking at the entire image. It's looking for the whole thing and then saying, ooh, I think a license plate is here. And then you have another one that says, like, I'm going to snip out only that section, and then I'm going to try to read the digits.
Yep. Well, it's going to scale it next. So you're going to snip out, scale it. You're going to make certain assumptions because you know what license plates look like about how to scale it. It's actually probably a nice problem because of that.
Fun problem.
Yeah. And then finally you can send it off to, your classifier after you've scaled and sliced and diced and now you've got something that might be able to output possible answers that you then display to the person driving. Hopefully they're not texting while they're doing it.
Yeah. So to build the data set for that, if you're starting out, it's like, hey, I want to build a license plate reader for that dash cam, but I have no data. What do you start doing? Strapping cameras to the front of cars, and driving around, right?
Yeah.
And then you send it off to crowdsource to crowdsource the data labeling, and you do it yourself, and you sit down and look at images, and you draw a box around the license plates. Oh, there's the box around the license plates, and you use those boxes, the pixel numbers for those boxes, to say like, in here there was a license plate. So that's to get the data to build your first model that just tells you where the license plate is. And then once you've gone through and made all of those boxes, now those are just images that are for your next data set that you go in and say like, can I read these or not? Or can a person read them or not? And then type in what that license plate is, the numbers or the letters. And now you actually have a labeled data set at that point, and that's how you train the models that we were talking about. Identify where the license plate is, and then also what is it, or what are the numbers.
And this is, keep in mind, this is all a very simplified version of this problem. This is.
Well, we don't have to make it more complicated, though. But it's super. This is a simplified version. Yeah. And it's already really complicated.
Yeah,
right?
exactly. This is a real world use case.
Yeah.
The real world is going to throw all sorts of kinks and curves at you. Like, for instance, I don't know, having multiple cars.
Yeah.
What do? You start detecting multiple license plates.
Yep.
What happens when a motorcycle splits lanes right next to you? What are you gonna look at there? Those kinds of things. Shadows hitting you. Those people that put the shields over their license plates to make them kind of hard to see, which I don't know the legality of that.
So a typical system that would identify like either where a license plate is or what the numbers are, that would be just like a typical CNN network, a convolutional neural network or something like that. These work really well. But those things have been done to death. Many academic papers written about them. You can figure out how deep should it be, how wide should it be, which kernels should I use, all these different settings. You can just go download one. You can just
there's
download
a lot of great
PyTorch,
stuff
TensorFlow, get an example, and there it is for you. And now it might not be trained for exactly what your task is, but you don't have to pick the model architecture. You don't have to go through that whole design process to figure out what's going to work or not. You can pretty much take it off the shelf and just hit train, maybe adjust a few parameters, but you spent an hour, 5 hours on that section, maybe a day, and then you spent 2 months on the other stuff, Yeah,
and that's a great point because there's a lot of off-the-shelf stuff that didn't exist before, especially in the image recognition world. If you're playing in that world, I don't get a good chance to go back there too often, but every time I look, there's just more and more amazing tools, especially when it comes to anything on the road. For obvious reasons, with the autonomous driving revolution that's happening, those tools are just getting a tremendous amount of attention, and there's a lot of great work that's out there. So, if you're thinking about building some of these things, look for off-the-shelf solutions first.
Yeah.
There
won't be an end-to-end everything you need to do, but there will be parts of it that you can save a considerable amount of time.
Yeah. But that again comes down to if you go with some off-the-shelf system, going into kind of things you should be thinking about. That might dictate some hardware that you don't have access to.
Yeah.
It's like this model here is using these tools, and these tools you either have to delve into them or figure out how to build something that can mimic them in some way, shape, or form. And that becomes a real concern, especially something like in a real world, you don't have a lot of processing power available trying to do this task. This comes back to the difference between accuracy and usability. If you have to have a rack of servers sitting in a car to be able to do the task, that's probably not usable.
Maybe a first proof of concept, but this isn't going to be a real product that you ship.
Driving around with all the fans whirring behind you.
Yeah, with $100,000 worth of computers in the back of your car.
It's great. I can read those license plates now. Although probably don't need that much compute for that task.
So we talked about data, super important. We talked about inputs and outputs, loss function.
Yeah, so this is really determining more the type of problem you're doing. Yeah. There's a lot of kind of standard. When we think about a loss function, what we're talking about is the thing that takes truth versus prediction and says how close are they?
Yeah. What's my error?
Yeah. What's my error?
How do I define what my error is?
And that loss function has to be crafted in such a way that It can work with auto differentiation, this ability to what we call back propagate the error all the way through the model. If you're talking about deep neural networks,
what does that do though? This is back propagation.
So back propagation, what we've got are all these. When we talk about a model, right? And model structure. The structure is sort of the physical way that the math is laid out. In other words, this equation leads to that equation, that leads to that equation. These are the layers.
These are layers,
right?
Yep.
These are the layers. But those layers, those equations, have a whole bunch of parameters. Mm-hmm. It's the simple, slope form mx plus b.
Just
right?
numbers.
They're just numbers. If you can get those m and b's just right, then you can fit the curve.
Yeah, and there's just like millions of them though.
But there's
a lot of
millions and millions and millions of them.
Yep.
So those things we call parameters. So when
all these dials in the network, and they need to be turned.
That's actually one of my favorite images is a person sitting in front of a switchboard with 10,000 knobs between 0 and 11.
Yeah.
And you've got every single one of those knobs affects every other knob.
Yep.
Right? And you've got inputs over here and you've got outputs over there. And if you could just twist those knobs to the right step.
There is a correct one that minimizes your error.
There is a great setting for them.
Yeah.
But finding that out. So what do? This is where back propagation and gradient descent and all these things come into play. You send something through that model.
You let it make a guess.
Let it make a guess.
Leave the settings where they are, but just go.
Yeah, and you look at the outputs that came in there, and you look at the truth.
Yeah.
And you have your loss
So you know
function.
the answer to the input that you gave it, and it's like how far away is the output from the model compared to what the actual truth is.
Exactly. And you've got your loss function that's going to show you that, and now from that loss function, I can look at each, I can take that error and I can propagate it backwards through that network. And
so essentially there's a recipe that says, if we have this error down here, then what you need to do is go back and turn all of these knobs this much.
Yeah.
But it's only a little bit, each of them.
Yeah.
It doesn't say, put this knob in this position. It says, move this one a little bit that way.
Yeah.
Move that one a little bit that way.
So in every single example that goes through that, it's going to say, hey, the knob should have been here, and the knob is going to be there. So when you've got a bunch of examples,
needs to be moved a little bit this way.
Yeah, you take the average of a bunch of examples at once. It's what we call a batch, and now the average says, in general, this knob should have gone over here.
Yeah.
And you do this a whole lot, and eventually you get
you don't do
settings
this
for those
once
knobs.
or 10 times. You do this like millions of times, many updates.
Yeah, exactly. It's in the end, it comes up with a great setting for those knobs, and now the outputs are getting you pretty close to what you want.
Yeah. At first, there's a lot of movement. The knobs are moving all over the place, and then there's just like slow refinement as the model starts to get trained.
Yeah, and the occasional time where it trips over and a whole bunch of them start going off in a little optimum.
Yeah, because they all affect each one of them.
Yep.
So, one, and and it has to make up for that change.
So that's generally back propagation. And, one of the key skills is sort of coming up with 1,001 ways of thinking about it to yourself. Because the more ways you start thinking about how this works, the better you understand, intuitively what's going on, and can help you design these things in the future.
Yeah. Constraints help a lot with this. How much money do you have? What computing resources do you have? What talent do you have? The people that know how to operate these systems. You can go down, or you can go on many goose chases here. A lot of rabbit holes. You could spend the next 15 years working on a problem and never come up with something that's actually valuable. And there's still many good things that you're learning along the way. You have to sort of learn to like cut off certain things and be like, good enough, good enough, good enough. And that's kind of the way that machine learning is now, at least. You have to have some restraint in order to get a real product out the door.
Yeah, definitely. And so we've talked a bit about designing something, but I think a lot of what people don't realize, again, with the machine learning world, is not just building as a challenge, but the world isn't static. Maintaining a deep neural network, is actually a really big challenge. I mean, even just consider a license plate problem. every single year, there's hundreds of new license plates. Someone does a write into Congress, or not Congress, but write into their local, representatives and say, hey, I think the state should have a picture of my favorite cartoon character from 1983. And they get enough signatures, and suddenly there's a brand new license plate in the world.
Yep.
And car designs change, vehicle designs change, all sorts of things change.
Or like in California, the first digit kind of just incrementally goes up, and so it's like there's a new first digit just because it's later on, and it wasn't likely before, but now it's likely. So
the idea that you put all this time and effort in and it stops. Maybe there are problems out there like that, but it's pretty hard to imagine them. We'll just go back to handwriting, the digit recognition. I can guarantee you that the average, penmanship has changed considerably in the last, 15, 20 years. So if you think that handwriting is stagnant, you're not banking on a good bet, I don't think.
Yeah.
So even such a simple task, you would think,
changing
I can gather
over time.
all this, but probably not. You need to have some way of keeping your model, keeping your environment up to date, and swapping it out, and keeping it trained and topped off.
Yeah. Also, presumably, you've got a model in production, and now what do you do with your time? You try to make it better, probably, right? And so, hey, I have some ideas. Maybe I could do this, or maybe I could do that, and that'll make it better. Great, but the other stuff is still operating over there. What if you make a small improvement? Okay, and so now there's like this version change history, and now you get into like version control of your models, which is not really a thing yet. People don't quite think in that way, but they certainly will have to think in that way in the future.
Well, that's a really huge challenge. There's some decent articles and blog posts on this fairly recently, talking about version control in the machine learning world, and that's just a big challenge. I mean, a lot of times we're talking about not just a few bytes of data here, but hundreds of megs, which doesn't sound like a lot, but
a gig or so.
You version that 15 times a day, and suddenly you're talking real data.
You're filling up your hard drive pretty fast. Yeah.
And the reproducibility of these things is, but it's a slight challenge, because you can take the same exact model structure, the same training data, the exact same training pipeline, and most of them incorporate randomness into them for very good reasons. So you'll get a different result if you train a model, twice with what you thought was all the same stuff.
Okay.
So what does it really mean to version control something, and is a big challenge.
Yeah, the question will have to be answered in the next few years, probably.
Yeah, this is really, we're seeing the evolution of the industry, and
Yeah, it is a long time scale thing. Hey, we're at the beginning, it's like electricity in the 1900s or something. That's AI now, right? So any final thoughts on building a useful neural network? Susan's key points.
Susan's key point. The key point is, you got to take real world data somehow. Don't get stuck in some training world.
You gotta use real world data.
Real world data. If you can't take real world data, you don't have a useful model, right? A useful structure. How about yourself?
Try to get water through the pipes.
Oh yeah, that's
just get something working, anything working, and then you can iterate.
Iterate.
Then you can iterate. And hey, maybe it doesn't work very well at first. That happens for sure. But then you tweak some things, and now it starts to work again. Yep. And is it all worth it to go through that?
Depends on the problem. Depends on the money.
Absolutely. Absolutely. Some problems are too hard. Just don't do it right now. Some problems are like really easily solved with something you don't need to use a neural network for. But there is a region in between where it's like, this makes a lot of sense.
Yeah. If you can get 95% of the way with a simple tool, maybe you
might
should be
keep doing that
first.
unless it's something you like make billions of dollars from, and then like, hey, maybe we can do something here. Okay. All right. Well, thanks for joining us on the AI show. What questions do you have about AI? Comment on YouTube or Twitch, or tweet us at Deepgram AI. We're Scott and Susan from Deepgram. We come in peace.
Certainly not robots.
100% not robots so far. See you next time.
All right. I'm going to beat you.
Here we go.
All right. This one's for real. Ready? 3, 2, 1, go.